Before you watch this video, please watch the related videos with introductions of three-dimensional vectors, the position vector, length of vector, very detailed videos I have done. You will find them all in the description box. After you have watched those videos, you can watch this video and it will help you. In this video, we will see the proof of resolution of vectors in three-dimensional space. So the theorem says that let I cap, j cap and k cap be the unit vectors in the direction of positive x, y and z axis respectively. What does that mean? You have here the x-axis, you have here the y-axis, and you have here the z-axis. In the x-axis, we have the unit vector I cap, right? And in the y-axis, we have j cap as our unit vector, and in the z-axis, we have k cap as our unit vector. And we know that unit vectors are represented by the symbol cap. And it has having initial point at the origin O. So they all have the origin at O. Let OP vector be the position vector of any point P in the space. So we have OP vector as a position vector in the space with P as the point. Then OP vector can be uniquely written as OP vector is equal to xi vector plus yj vector plus zk vector for some real number x, y and z. So this vector OP can be written in the form of I cap, j cap and k cap with a coefficient or a scalar multiple of x, y and z. I hope that's clear. Further, we can prove that the magnitude of OP, which is this length here, or the magnitude of OP is equal to the square root of x squared plus y squared plus z squared. So let's see the proof. So let x, y, z be the coordinates of a point P. So you have a point P with x, y, z as the coordinate. Let Q be the foot of the perpendicular drawn from P to the xy plane. So this is our xy plane. Okay, so this is a plane which with x and y axis. So you're going to draw a line from P which is perpendicular to the plane, xy plane. I hope you understand a plane. So it's coming perpendicular to the plane, all right, and it meets the plane at the point Q. So let Q be the foot of the perpendicular drawn from P to the xy plane. Okay, so it's the foot of the point P, PQ rather. Let R and S be the foots of the perpendicular drawn from Q to the x and y axis. Okay, so what does that mean? R is a perpendicular from the x axis towards the point Q, and S is the foot of the perpendicular which is drawn from Q to the y-axis. Okay, so you're drawing two perpendiculars, one to the x-axis, other to the y-axis, and R is the point at which the line touches the x-axis, and we call it the foot of the line. And similarly, this line's foot touches the y-axis at S. Alright, so that's so simple. Let OP be defined as vector R. So we're going to define this vector OP as vector R. Okay. So further, we can notice that our OR length will be x. Why? Because we said x here, right? The coordinates are x, y and z. So this length we know would be x. So similarly, this length OS, which is on the y-axis, would be y. And similarly, if you're going to draw a line here, perpendicular to the z-axis or straight to the z-axis, this point here would be z. All right, because it's a x, y and z. Next, further we can bring, or we can relate OR vector in terms of I and X. Since this length is X, which is a scalar quantity, and I cap is a unit vector of 1 unit. So this unit vector multiplied by X, the total length, will give you this full vector OR. Similarly, since the j cap is unit vector on the y-axis, multiplied by y will give you the vector OS. And it's also equal to the vector RQ because OS and RQ are parallel. Similarly, QP, the vector QP, is defined as Z and K because the length here is K is Z and the unit vector here in the Z axis is K cap. Next, let's define OP vector as the sum of OQ vector. So this is a vector, OQ vector plus QP vector. So you have OQ vector plus QP vector equal to OP vector or its R. Okay, so we have that here, OQ vector plus QP vector. That's very simple. Then the QP vector, which is the OQ vector. The OQ vector, which is the first one, can be expressed as OR vector plus RQ vector. OR vector plus RQ vector. Right? So the sum of these two vectors will be OQ vector. So we replace OQ vector with OR plus RQ. So we have that here. Now, our vector R is right now equal to OR vector plus RQ vector plus QP vector. Okay, so you see this like the steps. It comes like this, and like this. It's like climbing a ladder. So that's how the vector is represented using the sum of I cap vector, j cap vector, and k cap vector multiplied by the length. All right. So we can say that vector OP is equal to, or vector R is equal to xi cap plus yj cap plus z k cap. This OP vector is called the position vector of P. So the OP vector is called the position vector of P with respect to the origin O in three-dimensional space. In the triangle ORQ, so consider the triangle ORQ, right? So this is our triangle that I'm asking you to visualize. What do you say about this triangle? What do you think this triangle is? I'm sure that you're able to see that it's a right angle triangle. Yep, it's right angled here. So if it's a right angle triangle, my next question is, by Pythagoras theorem, what is the relationship between the sides? You know that, which is our OQ squared is equal to OR squared plus RQ squared, right? So we have that. OQ squared is equal to OR squared by RQ squared because this is a right angle triangle. Now, let's look at this triangle here. O, Q, and P. It's right angled at OQ, right? Since QP is perpendicular to this XY plane. So OQ is on the XY plane and it's right angled here. So applying again the Pythagoras theorem, we can say our OP vector squared is equal to OQ vector squared plus QP vector squared. So further applying that here, we say OP squared is equal to OQ squared plus QP squared. Now we have seen that our OQ squared is already equal to OR squared plus RQ squared, which is here. So let's replace OQ squared with OR squared plus RQ squared. So we have OP squared is equal to OQ squared plus QP squared, and we're replacing OQ with OR squared. So it is OR squared plus RQ squared. So OR squared plus RQ squared plus QP squared is equal to, we know this length is OR is X, RQ is Y, and QP is Z. So it's X squared plus Y squared plus Z squared. Now if you take the square root, or rather the magnitude of OP, which is this vector here, so taking the square, you can get this as square root of X squared plus Y squared plus Z squared. Alright, so the magnitude of a vector, which is a position vector, can be defined as the square root of the sum of the squares of the coefficients of I cap, j cap, and k cap. Further, we can see that the components of vector joining two points can be defined in the following manner. So let us find the components of vector joining the points x1, y1 to x2, y2. So let me call this point here as x1, y1, x2, y2. Okay. Next, let A and B be the points x1, y1 and x2, y2. So again, let's define this point as point A and this point as point B. Let P be the point x2 minus x1, y2 minus y1. So P will be a point with this value, which is the difference between x2 minus x1 and y2 minus y1. So it is going to be a position vector from O. So this is the origin O. But that would be parallel to AB. And so it will be a translation of the vector AB. So we can define AB as equal to OP vector, right? And the components of this OP vector are x2 minus x1 I cap and y2 minus y1 j cap. Hence, the component of AB in the directions of x and y axis are same as the OP vector, because we defined their parallel and they're equal in length. So it's the same as the OP vector. Similarly, if we translate this we're talking about a two-dimension, xy, and so we're talking about a two-dimension. If we translate it to a three-dimensional space of x1, y1, and z1, then the components of vector AB in the three-dimensional space will be x2 minus x1 I cap, y2 minus y1 j cap, and z2 minus z1 k cap. So that brings us to an understanding of how to find the components of any given vector AB when we know their point A and point B. Thank you for watching Maths Tutorial Anand. Please like, and you can comment if you have any questions, and do not forget to subscribe to get more videos like this.